So now we continue the course by discussing surface effects. And generally one can talk about two classes of surface effects on radiation. So if a collision cascade, which of course we now know is a bunch of atom collisions, happens to be near a surface, then one can either modify the surface or kick out atoms from the surface. And this kicking out of atoms from the surface has already been mentioned earlier on the course. That's called sputtering. And this damage production on the surface can have many forms. The simplest one is production of single extra atoms, adatoms, on the surface. This term adatom is a typical surface physics concept. And just to illustrate how this may happen, in this animation we see an incoming ion, in this case xenon copper, goes into a surface. It causes a collision cascade, which by now on this course should be rather familiar. But then at the surface, if you look what happens in the 3D image here, you see that several atoms are kicked out. In this case, if you count quickly, you can count that 7 atoms were kicked out in this particular event due to the collision cascade. And finally here you see that in the very end an 8th atom is, there is a late emission of an 8th atom here. So these are the sort of the base surface effects. And here we'll still show this 3D image of the same event on a larger scale. Now you can see how the collision cascades intersect with the surface, and then how atoms are actually leaving the surface, and a few are not leaving but then become adatoms on the surface, like this atom here for instance. And here if you look, wait a moment, you'll see that there indeed is one more atom coming out late in the cascade, so one can say that the surface is still hot and then one evaporates an atom due to the heat induced by the cascade. And here you see, for instance, one of these adatoms which were produced. And here is, for the lecture notes, the same thing as an image sequence, but since in this video you certainly saw the animation, this image sequence is not needed here. So now we will talk a little bit more about this sputtering, because sputtering is actually a big effect and it's industrially important. It's used quite widely in thin film, the coating of materials with thin films, which starts often with a magnetron sputtering. That this one has an electromagnetic field which heats up an argon plasma above a surface. This causes sputtering, which is then used for coating. And sputtering is indeed well known, and it's actually the oldest known radiation effects. The first scientific report which described with some degree of reliability the effect of sputtering was by William Grove, who published a paper in 1852 on sputtering. They didn't quite understand it was sputtering, but in retrospect, reading this paper, one can figure out that it must have been sputtering which was going on in this vacuum tube they made at that time. And the reason it hadn't been seen is that vacuum technology didn't really exist until the 1800s, when people started making vacuum tubes and doing scientific studies in them. And already in the 1800s, cathode ray tubes were used widely for electron emission, and quite often in cathode ray tubes you had sputtering. So it's been indeed known for a good while. There is a very simple measure for the amount of sputtering, which is known as sputtering yield, and this has already been mentioned earlier in the course. It's simply defined as the number of outcoming atoms divided by the number of incoming particles. In here, the incoming particle can in principle be any high energy particle. So the examples shown here are for ions, and indeed sputtering is most efficient for ions, and that's why it's often discussed for ions. It can also occur for electrons, high energy electrons, and even neutrons, but because the neutron cross sections are very low, this sputtering yield by neutrons are extremely small. And sputtering can be modeled, studied scientifically, theoretically, and with computer simulations by the binary collision approximations, if the conditions are such that there are no heat spikes, and then by molecular dynamics when there are heat spikes. And here is one more example of a sputtering simulation. This is by an 8 kV gallium ion hitting tungsten, in this case rather weak 315 surface orientation, which is a highly non-channeling direction. And here you see how the ion goes in. You see here we have cut out one quarter of the system, and you have a set of collisions which then lead to emission of atoms, quite a large number of atoms in this case. And the reason for doing these animations, actually quite recently, is that there were new experiments became available from the Max Planck Institute in Garching, Munich, where in the group of Martin Balda and Rudi Noy, they studied the crystal direction dependence on sputtering. And this had been partly studied earlier, already in the 1960s, but in this case, they have a method to study the sputtering yield over any crystal orientation. And it turned out that under some irradiation conditions, typically when you have heavy ions on dense materials, there can be a huge variation of the sputtering yield with crystal orientation. This was then also modeled both by binary collision approximation by Gerhard Hobler in Vienna, molecular dynamics by me, and we were able to reproduce, get essentially perfect agreement between the experiments and two different computer simulation methods, and all of them agree that the sputtering yields varies by more than a factor of 5, depending on which crystal direction you were impacting on. Moreover, there is no really constant regional sputtering. You see that there is a continuous variation of the sputtering yield pretty much everywhere for all crystal directions. Well, that was just one example of sputtering yield data, a new one, but generally usually not counting for the crystal orientation. There have been a huge number of experimental studies of sputtering yields since the 1950s. And here is a couple of compilations, a review book and a review article of sputtering yield data from different sources. And based on this data and some theoretical considerations, while people have been fitting analytical formulas which allow getting the sputtering yield for any ion in any element with fairly good degree of reliability, maybe 10 or 20% uncertainty in many cases. And there is actually a sputtering yield calculator available online at this address website. And just to give an example of what this, how much data there is, this is one of the images from this review article by Yamamura, where every letter in this plot is a sputtering yield measurement, and you can see from the number of letters that there is a huge amount of sputtering yield data. This is for the case of argon irradiation of gold as a function of the energy in electron volts. You also see that the data is not fully consistent. Note that this is a logarithmic scale. So for instance, the difference between this point and this point here is something like a factor of 5 difference in the data. So one can see that the experimental sputtering yield data is not fully consistent, and there are many differences to this. Of course, starting with experimental errors, but there can also be physical reasons which give a variation, even if the experiment is perfectly correct. One is that the implantation of the ion may change materials properties. Then this crystallinity effect, which was just shown a couple of slides ago, has usually not been accounted for in the experiments. Most of the samples are polycrystalline samples, and then you get an average over the sample surface. But if you have different grain orientations in the different amounts, that may actually affect the results, and so on. Also, there may be temperature effects, and so on and so on. So one has to review these experimental data with one caution, but like in this case, one can see that there is a large set of experiments which agree quite well with this fitted curve. So provided use that for an average sputtering yield over all crystal orientations, this average curve is probably quite reliable. Well, actually one reason why the sputtering yields can become quite large is surface effects of heat spikes. You saw earlier heat spikes that they can displace massive amounts of atoms, and this can lead to that if you are irradiating under a heat spike conditions, typically a heavy ion on a dense low melting point metal, one can get large effects from the heat spike on the sputtering. This was illustrated here on this case of 100 kV xenon ions on gold in this particular animation. The heat spike can also cause major surface effects which are much bigger than those just the adatom production. For instance, in here you see, if you compare the original surface, you see that there is a large amount of atoms which have been displaced to the surface. Then one actually forms a crater on the surface due to this heat spike which flows around the crater. And here is sort of an extreme example, gold 100,000 atom cluster impacting on gold, which can cause really big cratering effects. And here you see that what is the cratering effect by this quite large event near the surface. So this was a brief introduction to sputtering. As you may realize, sputtering is a big topic by itself and could even be worthy of a course of its own if I really would go into the details. But the most important for this course is that you know what sputtering is, and you know that for practically all elements and also many compounds, there is experimental data available which can be used to get at least a first idea of what the sputtering yields are. As a final part of this section 5 of the course, I'll mention what's known as subcascade breakup. That is, when one keeps increasing the ion energy or a neutral recoil energy, at some point you go into the regime where the nuclear stopping power goes down, which means that there are less and less nuclear collisions. The ions mainly go straight and slows down by electronic collisions. But every now and then you can have a strong collision, and when you have a strong collision, then you have a local heat spike and local cascade. And this is known as a subcascade. And this can be easily seen also from BCA simulations. This is a snapshot of a stream simulation of 100 kV argon on gold, and you clearly see that there is a number of subcascades, but then also segments where there is almost no damage, and then towards the end of the range, the subcascade becomes larger when the collision cross-section increases. And these subcascades can definitely exist, but then the question is that what energy do cascades start to break up into subcascades? And this energy at which cascades break up into subcascade is often called the subcascade threshold energy. And this sounds like there is a single well-defined energy when this cascade becomes a subcascade, but actually there isn't. It's not a well-defined single energy. It's a wide range of energies, maybe an order of magnitude wide, and it's not quite easy to define. For instance, if I look at these images of 10 kV cascades in silicon, germanium, aluminum, and gold, see that gold clearly it has a single heat spike at 10 kV. Germanium, would you call this subcascades or not? I wouldn't. I would say that this is a single cascade with some fractal features. But then on the other hand, silicon clearly has already at 10 kV subcascades, because you have clearly isolated damage pockets which form in this case, although one of them is pretty large. And aluminum again, this is really a matter of definition whether you call this thing here a subcascade or single continuous cascade. But generally this so-called energy of subcascade breakup, it's in low density materials it's quite low. In silicon one could it's below 10 kV, whereas then in very dense metals like tungsten and platinum the threshold may be as high as 100 kV. And rather recently there have been studies of systematic studies combining BCA and MD, which basically show, now without going to detail, that one can recognize a number of subcascades, that there is a regime where the number of subcascades start increasing and then goes into a linear increasing regime. So in this case one could say that the subcascade threshold is an energy regime between roughly 5 kV and roughly 50 kV in the case of iron. And similarly in tungsten, one could use also these different energies to split up, see how damage production changes when you go into the very highest cluster sizes, where you have have a single cascade, and then at lower energies when you are split into subcascades you have different kinds of damage. So the key thing to keep in mind about subcascades is that subcascades definitely exist at very high energies, but there is no single energy where a cascade split into subcascades, because everything is anyway stochastic, but there is an energy regime where you go over from a single cascade regime at low energies into many different subcascades at high energies. Finally, if you keep increasing the ion range into even higher, then we get back to the Swift heavy ion regime. I say get back because this was discussed in section 4 of the course. So in the Swift heavy ion regime, as you hopefully remember, damage formation dominated by the electronic stopping, the ion travels in a straight path, and binary collision approximation basically doesn't give any damage, because binary collision approximation cannot describe damage by electronic stopping. So this summarizes this entire section 5. Now I won't read this aloud, but I'll leave you a moment to read this, and if you do not remember what these things are, please go back and revise the material. Thank you and bye.